Record.
All right, so real quick, since you have done your math pre-assessment, you can look and see how you did. But a quick review of these concepts that should have carried over from previous science courses. First thing that you have to make sure you're able to do is convert using those metric measurements. So this might be using grams, liters, anything like that that may have one of those prefixes on it. So if you remember from previous courses, the prefixes, we have the King Henry died by drinking chocolate milk. Those are kind of our main prefixes that we use. Some of the other ones that you need to be aware of, above kilo, if you skip 2 spaces above kilo is mega, which is a capital M. And 2 spaces above mega is giga. So whenever you buy a flash drive, it might be in gigabytes. So a byte is another unit, but a gigabyte has millions of bytes in it, essentially. Same thing if you buy like an external hard drive, it might be terabytes, things like that. It's just another metric unit that we can use. So those are two of our larger units that might come up. Some of our smaller units. So we have like the King Henry died by is the kilo, hecto, deca. B is your base unit. That's going to be anything that does not have a prefix. So like grams, liters, meters, things like that. The lowercase d is deci. The C is centi. The M is milli. If you skip 2 spaces below milli, we have micro. It's a lowercase mu. So it almost looks like an M and a U with like a little tail at the end. And then 2 spaces below micro is nano. Sorry, I ran out of room. So this just gives you an idea of how many times you would need to move the decimal to convert from one unit to another. So looking at this first problem, going from centimeters to decameters, that's the capital D. You would kind of put your pencil on centi, so like put your pencil on the C, and then count how many times you would move the decimal and which direction you would move the decimal to get to that deca for decameters. So we would have to move it 1, 2, 3 spaces to the left. So here our decimal point is after the 0. So we would move our decimal point 3 spaces to the left. So it would be 0.250 decameters. So those are 2 numbers that are the same amount. It's the exact same measurement. They're just in different units. Doing the same thing for the next one. We have milliliters to liters. Notice that liters is a single letter. It does not have a prefix. So that is a base unit. So we're going from milli to the base unit. So that would be 1, 2, 3 spaces to the left. So 3 spaces to the left would be 2.068. I'm going to change this next example because I realized I had it moving 3 spaces as well. Let's look at how many centimeters are in, let's do 23 kilometers. So if we have 23 kilometers, that's our kilo, okay. To go to centimeters, we would have to go through hecta, deca, the base, deci, and centi. So that moves it 5 spaces to the right. So we would fill in all of those with zeros as placeholders. So that would be, oops, excuse me. So that would be 2,300,000 centimeters are in 23 kilometers. So simply pay attention to which direction you need to move the decimal and how many times you need to move the decimal. Another one of those skills that we use is a lot of our numbers in chemistry you will see written in scientific notation. So you want to make sure that you can recognize these numbers and write them in scientific notation, or expand the number if needed into standard form. So if you look at number 4, that write the 1.37 times 10 to the 4th in standard form. Standard form is the non-scientific notation number. So the regular number as we would write it out. So the times 10 to the 4th tells us that we moved the decimal point 4 times to put it in that coefficient in the 1.37. Because our exponent is a positive number, this means that this originally is a number greater than 1, so a large number. So in order to make this a number greater than 1, when we expand it, we need to move the decimal to the right. So if we move the decimal to the right, there we go. It's 137, so that's 2 of our spaces. We would then add 2 more spaces. So this is 13,700 is 1.37 times 10 to the 4th in standard form. Go in the opposite direction, writing numbers in scientific notation. So to write 0.0302 in scientific notation, the rules for scientific notation, you have to have 1 digit in front of the decimal point that is not 0. So the decimal point would have to move after the 3 here. So it would be 3.02. And then we have to designate how many times we move the decimal. So it's going to be times 10. And we move the decimal 2 times. However, this is a decimal number originally. So it is a number less than 1. So the exponent has to be negative to show that this is originally a decimal number whenever we put this in scientific notation. One thing we'll do a lot with scientific notation is we will do math with scientific notation. And you have to pay attention to how you type this in the calculator, or it will give you a wrong answer. Oh, excuse me, I don't have much room to scroll down. So to kind of show you how this is going to work, there are 2 ways that you can type numbers in scientific notation. One way is you can simply put everything in parentheses, because your calculator, whenever you type in the times 10, does not understand that that is one number. You're not actually multiplying the number by 10. It's just showing that the decimal has moved. So you can type in these 2 numbers and simply use parentheses for both of them. There's also a button on your calculator that is your EE button. On the TI calculators that are in the classroom, this is the button right above the 7, but it is a second function. So you have to hit second, and it's the comma button, that EE button. That EE is the same thing as times 10 caret. So that's going to be a button that's kind of a shortcut for you typing this in. So if you don't want to type the full numbers and use parentheses, what you can do is you can type the coefficient, the 2.3, hit the second EE button, and it pops up a single E on your screen. And then all you have to type is the exponent, so the -6. Then divide by and type in the coefficient, the 4.57. Hit the second EE button, and it pops up a single E on your screen. And then type in the exponent, the 3. Either way that you type it in, using the EE button or using parentheses, it will give you your answer in scientific notation majority of the time. sorry, my iPad's acting up. So whenever you get this, the calculator answer that it gives you is going to be like 5.0 times 10 to the negative 10th. And it didn't give us a unit, so we don't have to worry about adding that in. So these are all concepts that you should have learned in a previous science course. If you go to the very end of our Unit 1 notes, there are some additional slides on these if you need some additional help. So let's look over and look at our Unit 1 notes, the first part of them. All right, so at the very beginning of each unit notes, you're going to have some vocab. These are things that I would kind of highlight or make sure that you know as we go through the unit. So this is just something to reference back to. These are things that may come up on quizzes and tests, but a lot of times we need the basic vocab to be able to understand what the question is asking for. So you'll kind of see us use these and highlight these as we go throughout the unit, but this is going to be rather helpful to refer back to. So Unit 1 is just a basic introduction to chemistry. We are going to talk about what chemistry is. We're going to talk about a lot of the measurements and things that we deal with in chemistry. So looking at what is chemistry, and I'll full screen it for you so you can see a little bit better. So chemistry is the study of the composition, structure, and properties of matter and changes it undergoes. Chemistry is a huge topic. We are not going to cover all of chemistry in a semester. It's just not possible. There are different like subspecialties of chemistry as well. So chemistry tends to be divided into 5 different specialties or categories. And yet again, we are not going to focus on all of these. Even some of these are above the AP level and things like that. We do have organic chemistry. This is the study of all substances containing carbon that comes from living things. So this could be anything from human waste, human remains. It could be plant life or any compounds from plant derivatives and things like that. This organic chemistry is a little above what we tend to deal with. We will focus more on inorganic chemistry, tends to be what we deal with. This is the study of substances that do not contain carbons. They're not from living things. These tend to be more of mineral-based and things like that that we will go through. We're also going to look at some analytical chemistry. This focuses on the composition of substances. So we're going to be looking at what elements something is made of, the formula for that substance, how many particles are in that substance. So that's something that we will tie back into throughout the whole semester. We're also going to look a little bit at some physical chemistry. This focuses on the theories and experiments that describe the behaviors of chemicals. So looking at if we put these 2 chemicals together, what's going to happen? What are we going to observe? That will come up later in the semester. And then we also deal with biochemistry. Biochemistry is a little above what we deal with in our Chem 1 class. But biochemistry is the study of the chemistry of living organisms. So within an organism, what chemical reactions are going through. So this could be what chemical reaction occurs to help you break down and digest food, help you absorb nutrients. It could be dealing with like oxygenating your blood and things like that. But yet again, that's a little above what we deal with in here. I'm going to skip ahead. We're going to come back and talk about matter. We want to kind of focus more on measurements at this point in time. We're going to look at different measurements we deal with. these are going to tie back into those metric prefixes. And then we're also going to look at some of our basic calculations that we do in chemistry. So generally we focus on two types of measurements whenever we're collecting data or doing lab. Measurements can either be qualitative. These give results in a descriptive non-numerical form. So this is just kind of recording observations, what you see, or describing anything. So this could be an action. Maybe something changes color, maybe it bubbles, maybe it heats up, things like that. So just kind of a descriptive form of what is going on in the reaction. And then measurements can also be quantitative. So these give results in a definite form. So these are going to be number based, and they often have a unit with them. So if we were measuring a volume change that occurs, we would say maybe it increased by 5 milliliters or something like that. We would have an actual number and an associated unit that goes along with it. In chemistry, we are going to be doing both types of measurements. So you may be asked to describe what happens in the reaction, or you may be asked to actually measure mass, how much of a substance you have at the end of a reaction. So with science in general, but chemistry, we do have the International System of Units. These a lot of times are referred to as SI units. These are measurements that are metric based. So it's the metric system that has base measurements. So like our liter, gram, meter, things like that. And then using metric prefixes, we can get any derived units. So this is using those prefixes of the King Henry died by drinking chocolate milk. And these are going to be kind of the base units that we use for different measurements. But we can always change the unit using different prefixes to make it make more sense for whatever we're measuring. So length is going to be the distance between two objects. So it might be the distance from a desk to the door. So there's two kind of reference points we're dealing with. We tend to measure length in meters. Now, meters isn't always going to make sense for what we're measuring. If you're measuring the width of your pinky finger, that is not anywhere near a meter long. That may make more sense to use like centimeters or millimeters. Or I live in Kannapolis. It may not make sense for me to measure from Hickory Ridge to my house in Kannapolis in meters because it's a further distance. However, I can use kilometers instead of meters because it's a larger unit. It's going to make a little more sense for our measurement. With mass is the amount of matter in an object. This is going to be consistent without gravity taking place. So your mass looks at like how many particles are in this object overall. And it tends to be measured in some form of grams or kilograms, depending on the size of the object. Whereas weight is the force of gravity pulling down on an object's mass. So the force of gravity on an object, this tends to be measured in newtons. We tend to not deal with weight in chemistry. We tend to deal more with mass. Weight tends to be more like physics-based things overall and start dealing with forces as well. We can also measure area for a substance. This is the amount of surface on an object. This is a two-dimensional. So this would be just one flat surface that we're measuring. Area is a squared unit because we would have like length times width. So this might be in squared centimeters. If we're measuring the area of a house, it might be in squared meters, things like that. And then volume. Volume is a kind of three-dimensional measurement. It looks at the amount of space occupied by an object. So volume is going to be length times width times height. So we do have 3 dimensions here. The unit of this is going to be different depending on if it is a solid or a liquid. So liquids we tend to measure in some form of liters. So like milliliters we would use a lot. Or it can also be measured in cubic centimeters, which we tend to do for more solid objects. Note that a milliliter and a cubic centimeter are the same amount. So this will come into play in one of our later units where we do dimensional analysis, but they are the same amount overall. So this you may have heard of if you've watched any like medical TV shows and they're talking about giving medicines and they say we need like 20 cc's of something. Cc's is cubic centimeters. So that's the same thing as 20 milliliters. That's just how they tend to measure substances. And then also looking at time. This is the interval between 2 events. This could be from how long it takes from putting the chemicals together to when you see a color change or when bubbles stop or something like that. But you do have those 2 reference points, kind of the start and stop time that we're dealing with. Time does tend to be measured in seconds. But yet again, if it's a longer period of time, we can measure it in minutes or hours. But for a lot of our time measurements, it will be in seconds overall. I'm going to skip ahead. We're going to come back to sig figs later on. But some of the different measurements that are calculation based for us that we're going to deal with. One of them is density. Density is something that we're going to use several times throughout the semester. Density is the measure of the amount of matter that occupies a given space. So this takes the person's mass and volume to find density. This density formula is provided on your reference sheets. So density is equal to mass over volume. So if you have 2 of the measurements, you can figure out the other one. So you can use this to solve for mass or volume or density. Density tends to be measured in grams per cubic centimeter for solids or grams per milliliter for liquids. But yet again, it's going to be the same amount. An example of density, these are pretty straightforward problems. It's just being able to manipulate the formula overall. But here it says we have 10 cubic centimeter of a 10 cubic centimeter piece of lead that has a mass of 114 grams and wants to know what's the density of the lead. So it gives us the mass and it gives us the volume. So whenever we do the mass, the 114, divided by the volume, the 10 cubic centimeters, we get that the density of lead is going to be equal to 11.4 grams per cubic centimeters. Density is something that is unique from one substance to another. So like the density of lead is going to be different from the density of copper. So that's something that we can actually use to identify each substance. Whenever you're doing these problems, if you are not given a density, it is on your reference sheet. So on the front page of your reference sheet, on that left side down towards the bottom, there's a list of metals, and then it has their associated densities. So if it wanted to know the volume of lead and it gave you a mass, you can use the density on your reference sheet to help you find that. So we will be using this to identify different substances. And how densities are related, this kind of goes back to a little bit from earth science. But remember, if something is more dense than water, it will sink in water. So more dense substances will sink, they're heavier, whereas less dense substances will float. And then knowing how densities are affected by different situations. So looking at how temperature affects density of a substance. So this you dealt with in earth science as well, with like wind and ocean currents. We talk about hot air rises. So whenever we heat up air, it becomes less dense, which is what allows it to float or rise. Whereas that cold air is going to sink down towards the earth. So lowering the temperature makes a substance more dense. That may be affected when we talk about how different chemicals mix together. So let's look at this problem. And this is just another way that you'll see density problems. You won't always be solving for density. Sometimes it will ask you to solve for mass or volume. Volume tends to be the one that people mess up on the most, simply because they forget that volume is on the bottom of that fraction. You cannot leave it on the bottom when solving for volume. You have to kind of isolate that variable by itself. So here it wants to know what's the volume in cubic centimeters of a sample of cough syrup that has a mass of 50 grams. And it tells us the density of cough syrup is 0.950 grams per cubic centimeter. And like I said, you don't have to know different densities of substances. Either they will be given in the problem or they are on your reference sheet for you to go back to. So looking at what it gives us our mass of 50 grams and our density of 0.950. So whenever we plug this in, we have the 0.950 grams per cubic centimeter is equal to our mass of 50 grams over our volume. So like I said, you have to make sure to isolate volume and get it off the bottom. Let me change colors so you can see this a little bit more clearly. Okay. So we have to multiply by volume to get off the bottom, and then divide by the 0.950. So we have volume is equal to the 50 grams divided by 0.950, which when we put this in the calculator, we get 52.6, and that is cubic centimeters for the unit. Always make sure to include your units. That will kind of help you out, and especially whenever we get to some of our later units that we deal with. Later this week, we'll deal with rounding and things like that. So don't worry about rounding at this point in time. All right, another measurement that we are going to have to deal with is temperature. We're going to use temperature a lot throughout the course of the semester. What temperature is the measure of average vibrations of particles that make up an object. A lot of times we think of temperature as how hot or cold something is. What we perceive as hot or cold is the movement of those particles. So whenever we think of an object as being hot, that means the particles are moving very quickly. The particles are moving very quickly, and we're actually feeling kind of that kinetic energy overall. Whenever we perceive an object as being cold, those particles are moving at a slower rate for us. How we deal with temperature a lot of times is we will look at heat transfer or energy transfer. So temperature determines the direction of heat transfer. So heat always flows from an object of a higher temperature to an object of a lower temperature. So if you were to put your hand on your desk and it feels cold, that's because the desk is probably around 70 degrees while your body is going to be around 98 degrees. So there's actually energy going from your hand to the desk. So the desk is stealing energy or stealing heat from your hand, which is why it feels cold. We're going to deal with that later when we get to our thermochemistry unit. For temperatures, we tend to deal with the unit of Celsius. It's a scale that sets the freezing point of water at 0 degrees Celsius and boiling at 100 degrees Celsius. So Celsius temperatures are going to be lower than our Fahrenheit temperatures that we tend to use with English units. Celsius is what we're going to use during experiments, though. So our thermometers measure in Celsius, not Fahrenheit, that we're used to. We're also going to be dealing with the temperature scale of Kelvin. This we'll use for some of our math concepts that we'll deal with. But this is a scale that sets the freezing point of water at 273 Kelvin and the boiling point at 373 Kelvin. One thing to note that Kelvin temperatures do not have a degree symbol like Celsius does. And the Kelvin scale is based off of absolute zero, where all particle movement stops. So that's how we are going to go, or how we get the units overall. So we are going to have to convert between temperatures. You do not have to deal with Fahrenheit. You're only going to have to convert between Celsius and Kelvin. And this is using this formula. Excuse me. This formula that is on your reference sheet. So in order to get temperatures in Kelvin, you're going to take the temperature in Celsius and add 273. To go the other way, you would simply subtract 273. So for example, the normal human body temperature is 37 degrees Celsius. It wants to know what's the temperature in Kelvin. You're simply going to do the 37 degrees Celsius plus 273. And that gives us a temperature of 310. And our unit for Kelvin is just that capital K. And yet again, remember, it does not have a degree symbol. All right, last thing we're going to look at in terms of measurements is, are measurements accurate or precise? This is going to deal with when we have a series of measurements. So with accuracy, accuracy is the closeness of measurements to the correct or accepted value of what is being measured. So how close are we to the result we wanted or we should have gotten? So for example, if we are aiming at a target, we are aiming at the bullseye. So when we throw a dart at the target, are we hitting the bullseye or are we close to the bullseye? With lab stuff, say that we are measuring density and we know the density of, I'll use lead since we had that earlier. Since we know the density of lead is 11.4, when we measure it in lab, are we getting close to that 11.4? With precision, this is the closeness of a set of measurements of the same quantity made in the same way. And did we obtain the same results each time? So yet again, when we are shooting at a target or throwing darts at a target, are we hitting about the same spot every time we throw the dart? Or say that we are doing a lab where we're measuring density and we measure density 3 different times. Are we getting about the same result all 3 times? So you can look at the pictures here and notice the picture on the far left. The darts are not close together, so they are not precise. They are also not hitting the bullseye, so they are not accurate either. The one in the middle all of the darts are kind of clustered together, so it's precise. They're hitting about the same spot each time. However, they're not close to the bullseye, so they're not accurate. The picture on the far right, all of the darts are clustered together, so hitting about the same spot every time, so they're precise, and they're pretty close to the bullseye, so you're also accurate. So one thing you may have to do is gauge measurements. Are they accurate and precise? So are they close to what they should have gotten and they're accurate? Or if they did the same experiment 3 times, are they getting about the same results all 3 times? We will come back and do error at another time. You can actually start on the math section of your homework. It'll have you practice with those metric conversions, scientific notation, and go ahead and do some of the density and temperature calculations. Have a great day. I'll see you tomorrow.